and I'm recording. So Ed, I've got you unmuted, and then John, you can just unmute as you're ready. And we're recording, so you can go ahead and get started.
Okay. Hi, everyone. My name is John Ishii, and Ed Stringer's here with me. We're from the Seattle office, and we're going to be kind of doing an overview of the Inventor process that we've been working on for probably going on 2.5 years now. So we'll go ahead and get started here. So basically, this kind of started for us, like I said, probably about 2.5 years ago on a project this called Rainier Square here in Seattle. It's a 58-story tower, and what prompted us to start, one of the things that prompted us to start looking at Inventor for modeling and doing fabrication level work on the parts is this part of the building here that we call the Carve, which is a 22-story kind of chunk out of the corner of the building. So there are 157 units in that Carve portion. Out of those 157, 89 of them were unique. They all had, almost all the parts on all the units had some kind of a compound miter on the ends, and so we ended up modeling everything in Inventor and converting the files to step files, and then those went directly to CNC machine programming, which was done by an outside vendor at Hedro, just because our CNC machines didn't have the capability to make all the parts that we needed. So that's kind of where it started for us, and that was basically Ed and I did the majority of the modeling on all of those units over a pretty long period of time, because it was kind of a learning process for us. But so I'm going to turn it over to Ed here, and he's going to show kind of what some of that looked like at the early stages of when we started.
Can everybody see the Inventor?
Yep.
Okay. So this is our 3D model of the Carve. We put in the structure, and I don't know if this model has it or not, but we also placed some of our anchorage in the models. So this was pretty helpful in doing a lot of layout for the project. We started with a 3D wireframe that John built, and every unit is built to its specific opening, and then we use the points to line up all of the units in the end to create this final model here.
And that wireframe was developed in conjunction with the architect. We worked with them to, because on the corners where the curves come together, their original geometry had a lot of little tiny triangular pieces and things that couldn't be made. So we worked extensively with them to get the geometry optimized to a point to eliminate as much of that kind of stuff as we could. And then the other thing we did at the end for field is we worked with our layout guys to get 3D points for their total station off of it directly out of the model too. Sorry, go ahead, Ed.
This is what we called the mega unit, and it was the final unit to go in. John also modeled a steel frame that was, I think it didn't really lend structure to the unit. It was mostly for placing it and holding it all together as it was being put into place. And then we also modeled
Ed, your volume cut out on us.
I don't think I have it on right now, but we also had beams that we modeled in on the bottoms of the slabs to see if there was any interference. And I think we actually ended up making some adjustments to where the slabs were based on the interferences that we found when we were making the model. I remember sending templates to the contractors so that they could adjust where some of their beam work was. And I think they actually, some of their beams, they ended up notching so that the vertical mullions on the units had clearance to go through.
Yeah, they actually had, the steel beams aren't segmented to the same segment as the slab edge, and they hadn't accounted for the depth of the beams in some places and the sloping verticals. So they actually notched flanges out in places to accommodate that. But this was kind of the starting point for us, and it was a lot of trial and error on Ed and I's part. We were both learning Inventor and figuring out how to do this real complex geometry in it and get it so that we could fabricate. But I think that we had very few questions from the fabricator from the part files themselves when they were fabricating. And I believe when we got all the parts to our shop during the assembly process, Ed, I think there was what, like 1 or 2 parts that had issues that had to be corrected. Everything else went together.
Yeah, and I think the corrections were pretty minor as well.
As it should.
And the field was also, from what I heard, was very impressed with how it all went together, considering that we didn't make fabrication drawings.
Yeah, and believe it or not, that top unit went in probably quicker than some regular corner units. I mean, it slid right into place after putting that many units in with that kind of geometry, and that big thing slid right into place without any problems. So I think this whole process kind of cemented for us going through this job and how everything worked, that this is going to be a good process for us going forward. I think it significantly improves the accuracy for us on a lot of stuff, and I don't think we would have been able to do this particular part of this project without it. So that's kind of where it started. Since then, you know, we have an initiative in the company to try and move away from just 2D into this 3D using Inventor. And as we've been working on it, we've been kind of taking a lot of baby steps. So that led us to look, as we got more experienced, we looked for opportunities to work on this using smaller portions of things, and that visual mockups was the first thing kind of that came out of that. And we've done, I don't know, probably 4 or 5 visual mockups now that have been fully Inventor modeled, and parts going directly to our programmers in step file format. So that's been one of the things that we've used it multiple times since then. So I think Ed's got 1 or 2 of those to show just kind of what those look like and talk about.
This is Dexter Yard. I think this is the first mock-up that we actually modeled with Inventor, and we modeled the steel frame, the chamber steel for it to be mounted on, and figured out all the connections with that, and modeled full units from the project. It really helped us figure out how things would go together and see what kind of interferences we would find when we went to go fabricate parts. And then the next one was Yale and Harrison. And we didn't model the steel framework for this, but we had some soffit panels they're gonna move the mock-up to another site and install these soffit panels so they can get the full feel for how the project will be. And so the panels actually that are on this project, we sent them as step files to the vendor to make for us. And they seem to go pretty well with that format. We had to have conversations with the vendors and see what their capabilities are. They made Fab drawings from our step files and then sent us the Fab drawings for approval.
And one thing we learned going through some of these mockups is that working with the guys in the shop and the programmers is that, you know, they were a little skeptical at first, but once they started getting step files of parts, they really like it and have found it to be very useful and quicker in a lot of cases than the old way of doing things. And so the more we get and the more experience they get using them, I think the better it's going to be. So then the other thing that we've done is look at areas and done any kind of transitions or 3D modeling that we would have previously done in AutoCAD, and we now pretty much do that exclusively in Inventor. So we've got just some examples here of this is one of the Amazon buildings that we did, and this was just to solve some complicated transitions. And this particular stuff was actually, this project was fabricated by Phoenix, and so we sent some of these transitions directly to them, and well, I think we converted it to AutoCAD format, and then they used those to make the part drawings off of it for this particular case. But what that's done is it's given us and the people in the department a lot of practice learning and using Inventor. And even though we're not, like in a case like this, we're not directly going to the CNC machines off of it, it's given us a lot of understanding of the capabilities and a lot of practice.
This is a model I made of a light monitor interacting with our curtain wall. And the coping changes directions, and there was some questions about how all of that was going to interact at the framing provided by the contractor. So I put some of our units in and then created the copings, and then where visibility. So then we can see how the steel underneath there interacts with the framing and how our coping interacts with the framing and what other interferences we would have there. And also finding with our starter sills, we actually found that we were going to have to notch our starter sills some so that the coping could interact there and be sealed sufficiently. And I think the field guys, our field superintendent was using this the other day to look at things and try and figure out how it's going to go together once they actually are installing on the project.
So those are just some samples of stuff that we've been doing. And while all this is going on, we've been developing a process for the modeling and how we want to do that. And there's several things that are involved. I mean, making the models and the parts is, once you learn Inventor, is fairly straightforward, but then in order to fulfill a lot of the other things that we have to do, you got to make sure that you can get the data into the models correctly in terms of, you know, part numbers and finishes and materials and all that kind of information. So there's been a lot of time that we've spent trying to figure out all of those. We've been documenting the different processes that we're using, and then figuring out how to take that to be able to create, you know, unit drawings, part drawings when needed, and different things like that. So this is kind of just a brief list on our current processes. We're going to show you some of these, but essentially we're using what's called a multi-body solid modeling technique for the units themselves, for the most part, which is the unit is created in one part file right now, each different part is a different solid. And then from there, that you can convert them into individual parts. And then we've got some iLogic automation that we're using to import data into the different part files and then create unit drawings and some things like that. So, and then the last thing that's listed there is, so currently right now, in terms of part numbering is kind of the big thing that we don't have currently figured out. So what we're doing is using a hybrid approach, and we're using the takeoff program still to assign part numbers. So there's a little bit of extra work there, but that gets us our part numbers, and then those get assigned in Inventor. We're working on some different things that we'll talk about in a little bit that to go away from doing that. But I think right now Ed is going to start off and kind of show you some of these first items here, demo some things, and show the processes that we've got set up.
So we start with our wireframes as our basis for our unit, doing the takeoff and making unit drawings. So I've created wireframe similar to what we use for our current process. And then we add planes to those that we do our extrudes from and to in our Inventor process. And we also add parameters, user parameters to the wireframe that control the size and configuration of the wireframe. So these dimensions here are driven by those parameters, and there's, depending on how the wireframe is configured, you place them where they're appropriate. And then those can be used to set up a unit configurator, which you can do your unit type and the mod width and mod height and the placement of the intermediate horizontal. And there's a lot of little things in here that you can adjust. And they aren't necessary, but it's nice to have because it makes it so that you can take one model and adjust it a lot and get a lot of very unique units out of it. I'm going to take you through the process of doing an extrude, and then I will show how the configurator works on a model that's been partially modeled because it shows it off better. So this is a partial unit that we built, and I'm going to put in the intermediate horizontal.
Hey Ed, will you explain just a little bit about the sketch blocks, and so that just so that it's show how we get that stuff in there?
So typically with Inventor, you create a sketch and then you would extrude that. So, and you can create blocks within Inventor, kind of like the AutoCAD blocks. And so what we do is take our AutoCAD profiles of the dies and create sketch blocks in Inventor of those profiles so that we don't have to constantly sketch them in here or drag them from the AutoCAD drawings. So I've created a library in this template of parts that are specific to this project and given them either, if they're a unique die to the project, then we name them accordingly. And then we also have system dies, and the idea is that for each project, we would have a template that has all of our system dies that would be used on that project. And then we build up the library for that project of the specific dies for that project. And then that way, when people are making the model units, they don't even really have to think about it. They can just go over to this browser here and add that to a sketch.
Will you open one of those just so they can see what it looks like?
So this is the block, and you can edit in this like in AutoCAD. You go into the block editor and you can change things. There's limits to what you can do because it can kind of destroy some of the extrudes within Inventor, but you can do some minor changes here. Like AutoCAD, when you put a profile in here, it's protected from being edited unless somebody actually intentionally goes in and works on it. So I typically don't fully constrain the profiles in here like they recommend in Inventor sketching, but I feel pretty safe with that people aren't going to randomly jump in and make edits to these. So it'll save the change. And then you would go to do the sketch and place it on a plane and use you could do project geometry, which means that you can make this line on the wireframe be a reference geometry inside that sketch. So you can click on that and it'll give you a spot to basically constrain things from. So we'll do this one and then we'll do the vertical DLO line. And then you can come over to this browser and right click and then go place block. Another plus side of the blocks, if you use a place block, is if you've created an insertion point, you can hover over until the dot turns green and then click, and that actually creates a constraint right away. And then you go up here to the constraints palette and grab this constraint here, click on this profile, and then on the projected geometry. And the profile, when it turns dark blue, it's fully constrained. It can't be moved around or manipulated after those constraints have been placed. You can go in later and show all of your constraints, and you can delete ones if you're having problems with constraints and redo them if need. But so after that's been placed, you click the finish sketch, and we're going to extrude this sketch to this plane here and this plane over on the right hand side. So palette comes up and you click on the profile and select new solid. If you don't select a new solid, then it basically blends this part in with it. If it's based off another part, it'll make it as being the same part rather than separating it. So we want to create the new solid and then select the planes that you're going to extrude between. And then click OK. So now you have a new intermediate horizontal. And then the configurator is made so that I have five typical units: a left jam, left outside corner, right jam, right outside corner, and a typical. So if we go with a left outside corner and hit apply, it'll actually tilt the planes and miter the horizontal members. And that makes it so we only have to, if we're doing an outside corner unit, we only have to replace the actual outside corner mullion, and we can keep the rest of the parts as long as they work with that unit.
And that's part of the reason why everything is set to extrude between planes that we've placed in there and control with the parameters, because you could, while you're extruding between things, you could go from like side of vertical to side of vertical. But then if you go back and you have to make a change to something and that vertical for some reason changes, then it will break links in the model because that plane that you've extruded to, which is the side of the vertical, isn't there and may not be there anymore. So that's why everything we try and set up to go between planes that we've placed specifically on the wireframe geometry and controlled by parameters, because then it significantly reduces the risk of things becoming unconnected to one another.
The configurator also allows us to change the size of our units. Just as an extreme version of what's possible. This one's set up so we can change the mod width, height, the intermediate horizontal height, sill height when we have dies that are different heights. And then this one's also set up so that when we do the infill sketch on here to extrude the IGUs, we can actually change the bite of the glass on the verticals this way, so that if there are any changes, we have a project, sometimes we have projects where the glass bite's going to be a little different on one side versus the other, then we can go in and change these. And I've also, on some of these, I've built a multi-value list, meaning you can go in and choose preset sizes of items, and then that way you're not just, if you won't accidentally type in a number and get some random number that doesn't make any sense. I think that's it for this.
All right.
We do have a chat comment. Finding a way to extract the grid data from the architect's model and directing it into that size would be very nice.
It would be. That's assuming that the architect's grid model is correct. That's what we run into a lot of times, especially on the jobs that we work on. We start so early in the process. A lot of times the architect's models that we're working with are pretty early on in the process. So it's sometimes hard to rely on that. But it is something that we've got kind of as a goal out there in the future to get it to the point where we can extract information from architects' models as much as possible. Okay, so I'm gonna, I guess, Ed, if you stop sharing, then I'm gonna take over here and kind of show the next part of the process. Okay, so can people see my screen?
Yeah.
Okay. So basically, this is a model that is fairly complete. I think this particular one, it's not completely fabbed and stuff. This was just some testing that I've been doing on. So it's just got the lengths and stuff correct. It's not fully complete, but for the purposes of what we're going to show here, it works. Basically, when the model is done in this form, it's a single part file, like we mentioned. And I want to say that it's kind of a dumb model at this point. It's got the parts and stuff are the right size, the right geometry. It would, in most cases, would have the correct fab and all that kind of stuff, but it doesn't have any of the data into it. It's not broken into individual parts. And that's all stuff that we need to get to fill out bill of materials and all that kind of information. So the first step in the process is taking this single part and breaking it into individual parts for every part that's, individual files for every part that's in here, which is a fairly straightforward process built right into Inventor. It's make components. And what you do with that is you go in and everything that's a solid body that gets extruded separately is listed over here in the browser. So we just want to select those. It adds it to this here. And you give it a target assembly name, which in this case, the assembly is also going to be the unit number that's been assigned. You can determine what kind of BOM structure you want. In this case, normal. There are some things like reference. So you can have parts in the assembly that don't show up in your bill of materials if you want, which will happen here in a little bit. And then there's some other things you can reference things as purchased or things like that. We're only going to really deal with the reference and the normal. So for all of these parts, they're going to be normal. And then you can determine what template you want. In this case, we've got a specific template set up that's got some information in it that we're going to use here in a minute. So we'll select that. Then it just gives you a list. You can go in here and you can change component names and sources and other things. In this case, all of these solids are already named to the part numbers that they've been assigned, the mark numbers. So everything is good here. Then when we hit OK, this is just a style conflict that that is because I'm not working off the correct project file in this case. So here it created an assembly, looks pretty much the same. The difference is now everything is a separate part file over here. You can open it individually, and there's just the vertical. And the other thing that this did is it's got some parts here in the tree that were already included. These are not actually modeled, and you can see the different color here, this little purple box. What those are is those are virtual parts that were set up in the template. So those represent things like anchor lugs and lifting lugs that are the same from unit to unit. So we don't want to take the time to model it. We have kind of master part files for those, part drawings for those that we're not going to create and model every single time. They're just the same from job to job. So those will just reside in the template. But this way they will show up in the bill of materials and be counted and all of that. So I'm just going to save this here. You save it, and now you can see it's creating. It's the initial save for all these new parts that we created. Then the next step in the process is getting the information in. And so we've created all these different iLogic rules over here, and they each do something different. And so I'm just going to hit right click and hit run all the rules, and it's going to go through and it's going to go through each one of these and go through the code and do what it's assigned to do. And as you can see from some of the names, they're pretty self-descriptive. But so this first one is copying some of the parameters from the initial part that Ed had set up, because we're using that in some of these other rules to do things like determine the number of setting blocks and setting chairs that are needed and the lengths of some of these lineal gaskets. So then it's gone through and it's run all these. You can see it added a bunch more virtual parts over here. And these are things like our AL13 rod at the chicken head, the setting blocks, setting chairs, and then gaskets. And what it's done for the gaskets is it's given it a part, but it's then calculated the length of that we need based on the mod width and mod height. There's formulas set up in here. And then some of the other things that it's done is, so this rule here that's add part properties. Again, it's just some code, but what this one is specifically doing is it's using an Excel file. And so it's opening an Excel file that we've created. And this is where most of our data is going to reside. So again, this is a small version just because it's some testing that we've done early on, but it's got the part number and then the extrusion and some other information that we need: material, temper, alloy, finish, routing, which is for us, determines what part of our process that part goes to, description. And then we've got the same thing for some of the infills here. And then it's also got job name and job number in it. So this rule here is searching by part number, and if it finds a part number that matches the part name in that Excel spreadsheet, it adds the different properties to that file for us and fills in that information. And so that's really what all of these are doing here. It's just, it's just different code that goes through and it looks at different data that's in here and then fills in other things, or in this case creates virtual parts for us based on information that it's pulling from other places. So now we've essentially added lots of information to these parts that were just the part before. The other thing this is doing is it's getting the part sizes for us and the infill sizes, so that those will show up in the BOM and be listed for us. So again, we'll save this now that it's got all the information in it. And then the other step of this process is if we go back to the original file, we have one more thing that we need to extract from this that wasn't done before. And so we're gonna, if I go make part here, there's some geometry that we need to pull in order to help with the automated unit drawing process that we've got. And that's, we've created dimension points, which is just a point. And so I'm going to pull those into and create a part that just has those in. So I'm going to just name that and then this one is just going to be a reference because I don't want the part to show up in the BOM, and I don't need to place it in an assembly. So literally all this is doing is it's creating a part that's just got these points that I created those are all based off of mod points or dimension points that we want off of the original wireframe. So when I save that, it creates a part. And then if I go back to my assembly, I'm going to just place that in here in the correct place. That's not what I wanted. So there's my wireframe. I'm going to place that grounded at origin, which is what the rest of it is. But as you can see, so that's putting the points here at places that we're going to use to put dimensions on the unit drawing automatically. So it's basically mod height and mod width and then DLOs. So that's in there now. Our unit drawing is basically, or our unit model is basically complete. It's got the information in there that we need. Next step of the process then is to make our unit drawing, which we've got fairly automated at this point. I'm just going to create it. I've got a unit drawing template set up here. So again, I've got rules set up and it automatically opens up an open dialog box for me. So it's wanting me to pick which unit drawing I'm going to make. So I just select the unit here. It places everything for us automatically. So it's placed the view, the elevation view, a plan view, all the dimensions we need, and our parts list. Parts list is sorted. It's got all the columns with the information that we need for this particular unit that we use. There are some things that we're still working on trying to get automated on this. There is detail bubbles is one of the things that we haven't done yet. So we can, we'll still have to go in and insert detail bubbles by hand at this point. But those are sketch symbols that are built in, and you just type in the detail. And then the other component is annotating the parts. Inventor has a auto balloon built into it that you use, or that you can use, that that will do it for you to some extent. It's not the this is part of what we're still kind of working on at this point. And I'm not even remembering, what did I not do here? Oh. Add or remove components. What did I not select, Ed? I'm missing something.
I don't know. I haven't done this as much as you have.
Oh, there it is. So then you can go and you can move these, and there's some simplified ways to do this, and it's actually not, I don't have the style set up right for this yet, but essentially what this is doing is it's locating every one of the parts in the model and tagging it for you. It's still kind of a work in progress. What this will be set up is it will be set up to call out the part number. We would like to get it to the point where it will be part of the automated process. We're not there yet, but that's kind of where we're at with the unit drawings. So I am going to turn it back over to Ed here.
Okay.
So this is kind of just where we're hoping to go, things that we're still working on that have to be done. The part numbering, like I mentioned before, is one of the big things. We're working with a company called D3 Technologies right now to develop that. And that's, so they're going to be working on custom programming for us using both Inventor and Walt. We are using what's called Walt Professional, which is a data and file management system that Autodesk uses or has. And it's basically, you can check in and check out parts for working on them, and it keeps track of things like revision control, and it's pretty powerful. It can do a lot of things in there. So we're working with them to come up with a process. Probably it'll be something like once we make the unit, make the single part into a unit with all the different parts, it'll search the vault to see if existing parts match and then replace them or assign a new number. But that's currently in development right now. As I mentioned, we're some of the unit drawing process and probably part drawing process we're looking to automate a little bit further. For part drawings, Inventor has the ability to save view locations and things, so that if we pick a part, it'll automatically know which views to place and where to place them on the sheet. So those are some things that we're continuing to look into and hope to develop further. And then some other things that we still have to solve are material optimizations. We briefly looked into, there's another utility add-on that Inventor has that's called nesting utility, and we think it's capable of doing the optimization, and Autodesk has done some videos for us to show us what it can do, and kind of tested some things out for us to show us that it's possible to work. So that's something we're going to work on further this summer. And then further down the road, once we get the Fab Drawing process and the fabrication process signed out, we hope to start using this to make the models early on and have that incorporated into our shop drawings, so that all the geometry is created directly from the models. And then the other thing that's listed there is factory design utilities, which is another add-on. Is a add-on that's meant for designing factory layouts and things like that, but it's got some unique functionality to it where we can take a unit model and we can add what they call connectors to it, so that it's easy to place units and kind of go around the building and place them where they need to go. Typically with Inventor, the way that you assemble things is you place parts together and then they have to be constrained in all three directions. With these connectors, you can basically shortcut that process by building that into the unit, and then it's kind of a drag and drop from one window to another. You can which unit you want. You build a library of these with the connectors on them, and then you can just drag the units into place, and they kind of snap right into place. So those are all things that we're looking into and hoping to incorporate here in the near future into the process as we move further and further along. We're just getting ready to start doing our first job using this for fabbing and fab drawings coming up here in the next few weeks, actually. So anything else you want to add, Ed, at this point?
No, I have an example of Fab Drawing that I could share and talk about that a little bit if you want.
Okay.
So this is a Inventor-based Fab Drawing. You can place the part on one view, and then basically you can drag out views that you want placed, and it'll drop them in there. This is actually the part, and if you modify this part, those changes will update in your drawing as long as you're using an Inventor DWG. And if you have a part that's too long, say you've got these break lines here, if we wanted to have a dimension here, Inventor, the DWG is smart enough that you can put your dim line on this point and on this point, and it'll give you the dimension of the actual part, because it already knows what the length of the part is. But if you throw the break lines in, it accommodates for that. The other features we have is down in this title block here. These numbers are actually, some of them are driven by the properties that the Excel spreadsheet is driving to the, well, actually all of them are now driven by that. All these part properties are driven to the parts, and then when you drop the part file into the drawing, it fills out these boxes automatically. So if you have a project and all those parts get the project name and number, and then the extrusion number, and then I think we're still working on how to deal with fab numbers, but we'll see how that goes. I think that's it for that.
We do have a question in the chat. Can you show an STP export from your example unit? Does it have screw spline holes for attachment?
We could open one up, but it's just going to open Inventor, so it's just going to look like an Inventor part. But yeah, Ed, do you have like a fab vertical or something that you can show that it's got everything in it anywhere? That's probably not handy, huh? But that's something we probably didn't plan for. But the short answer is, yeah, the STP file is good. It would import back into Inventor in the same look. It imports in the CAM Plus software. They can import the STP file with driver CAD in directly, and then it'll auto recognize a lot of the machinings that they need to use also. But in terms of what it would look like, it would look just like a fully fabbed vertical, or the unit that I showed wasn't complete in that sense, but typically, yes, everything will be modeled to the exact way that it needs to be fabricated, with all the holes, notching, cuts, everything in it.
The difference between the step file and the IPT file of Inventor is that the step file, once you open it, it's not as easy to modify hole locations and notches. There's ways to do it, but they're just not very convenient.
Okay, so in the questions, I actually had a question about when you have your unit, which is kind of ready for creating the fabs out of it. Is there some kind of a crash detector that's happening there where you could see if one part is like intersecting something in a weird way, or something that you wouldn't expect that you want to see happen in the fab tickets?
There is. Can you?
I could do some of the model.
So they have, so there's in Inventor, there's a built-in thing that's called interference detection, or
Analyze interference.
analyze interference. So any assemblies, anything that you have open, you can select different parts, and it will do that for you automatically, and it'll highlight the areas. It'll show you, I think it'll tell you what area is interfering. And that's, so what a funny story about this carve is, this model is actually kind of Carve 2.0, because we actually had most of it modeled and then started using this tool and found that we were doing some things incorrectly in terms of the placement of the units and the geometry. And so we found it best to start kind of over again. But this tool was one of the ways that we determined that we had a problem with the way we were doing it initially. So
these red lines are literally just that's the two mullions interfacing together. That's showing just that minor interference of those.
Yeah, that's the male female snap engagement, just where they, when you put those dies together and they overlap a little bit to give that snap, and that's what it's showing.
And that only works in the assembly environment. It doesn't work in the part environment. So this is something you would have to do after you've converted the file from the first file that John was showing to the one where all the individual parts are actually in existence at that point.
But if you found that you had a problem, and you can always go back to that original part file and make adjustments to it, and then it will automatically propagate through and update the assembly and all the individual parts.
Very nice, thank you. And you're open for other questions from the group, right?
Yeah.
Are you guys hiring?
Always.
Your stuff looks like so much fun.
Yeah, this particular building was a pretty interesting one. We've got a couple of other ones coming up too that should be that are pretty massive projects with some crazy stuff going on.
Okay, any other questions from the group for John and Ed?
Can you have multiple people? What did that say?
So Chris's question is, can you have multiple people work on an assembly? So one of the reasons he's asking is we use the takeoff database, and if we have more than one person working on it, it creates a lot of problems for us. So we actually have created methods to try to do that, but just one person at a time in the database. So
a lot of that will be controlled by Vault. So that's got a check-in, check-out process. So with the way that we're doing it, I mean, only one person will probably be working in a unit at a time on a per unit basis. And in terms of like building an assembly of the whole building or each floor or whatever, I don't think that you can. Well, you could, but the way Vault works is like if you wanted to work on a file, whether it be a part file or an assembly, you check that file out of the Vault, which then, so somebody else could check that same file out, but once it gets checked back in, it's only available
You can't actually check it out more than once. Once it's been checked out.
Oh yeah. Once it's been checked out, you can't check it out again. You could get the file from Vault and work on it, but you couldn't check it back in yourself. Only the person that checks it out could check it back in.
But if you have an assembly and a lot of other people are working on units that are part files, not assemblies, I think in theory, if one person was working on the assembly, they could be grabbing those units and dropping them into the assembly. They just wouldn't be able to modify the part files themselves if somebody's working on them already. But the plus side is that any changes that person, the other people who are working on the individual part files, those are cascading into the assembly as well. So they limit, the Vault is limiting it to one person per file, just so that there's no second copies floating out there. There's only one version of the truth floating out there.
And then Sherwin's asking, do you use iLogic?
Yes, we do. So basically, all of the stuff that I was showing in terms of getting the data into the parts and into the model, and then the auto creation of the unit drawings, that's all iLogic based. So every one of those rules that I show is an iLogic rule that did different tasks. And so we've I want to say written, but we haven't really written them. A lot of this stuff is available on the Autodesk forums that people have either already done or done something very similar, and you just kind of grab it and adjust it to make it work for your situation. Because neither Ed or I are a great programmer. So it's just been a lot of hunting and pecking for things, and then a lot of help from people on the forums who are great, that if you can't get something to work just right, you post it on there and they'll give you suggestions or help you fix it so that it does work. So honestly, a lot of that stuff has come during this COVID work from home. I've had a lot of free time on my hands and been able to put a lot of this stuff together. So it's, in that sense, it's kind of worked out good for us.
You can use a lot of basic iLogic to drive the configurator that I was showing too. So like with the unit types, if you say, well, this unit type, these parts are going to be on, or these planes are going to be this way, you can write pretty easy code that'll do that. And so you just click the drop down button and select the type, and it says, oh, well, you want these planes here and this stuff here, and it adjusts that. And that's basic iLogic that isn't that hard to write.
Great. Any last minute questions?
Thank you, guys.
Looking good. All
Thank
right,
you
John,
for
Ed,
having us.
thank you very much. Appreciate the presentation. You guys did a fantastic job.
Good job.
Thanks, guys.
Really cool.
Thank you, guys.
Thanks.
Thanks for showing us that.
Thank you.